The whole idea behind hashing is to try to speed up the searches of a large number of items. Let's say, for instance, that I have a bunch of items in a database and I'm going to have to search on the last name, or I'm going to search on a phone number, or I have some sort of an index value that I'm trying to search on. If I'm looking for one single record out of 100,000 records, the length of the field that I'm searching on can make a huge impact on how long it takes me to find that individual record. Let's say, for instance, I was searching on phone number, which is a 10-digit field. Doing direct comparisons for 10-digit fields is pretty tedious. But if I was searching on zip code field, which was only 5 digits long, it would those direct comparisons between 5-digit fields would speed up the searches. The idea behind hashing is that I can take my original search value and I can create a much shorter field that I can search on instead of my primary. All right, so let's do an example of this. Let's say, for instance, that I wanted to store students in a database by their W number. And the W number is 8 digits long. In order to search through 8 digits and do exact comparisons, I'm going to have to search through almost 100,000. Do a comparison between numbers that are 100,000 in length. That is a very, very large number. But what if there was some way that I could search for, or I could assign, let's say, for instance, a 3-digit number to each one of those students? Do you think that it would be faster to search 3 digits to do exact comparison between 3 digits than it would be their original 8 digits long? That idea of finding that smaller, shorter value is called a hash algorithm. So let's say, for instance, that I wanted to assign a 3-digit number to each of the students' W number. There are a variety of different algorithms that I could come up with. One of the algorithms might say take the largest possible number that's possible out of 8 digits. 1, 2, 3, 4, 5, 6, 7, 8. That would be a 8-digit W number. And I'm going to divide that by the total number of students that I might ever have in my database. So let's say, for instance, that I'm a small university and I'm going to have 2,000 students in my database. If I do this division, I'm going to come up with 49,000. This is going to be my hash value, 49,000. So now that I have my hash value, let's take a W number. Let's say, for instance, 1, 2, 3, 4, 5, 6, 7, 8. And I am going to divide that by my hash value. This is going to give me 251. This is going to be the hash key. And so I'm going to associate 251 in my database with that particular W number. So instead of searching for through an 8-digit number, I only have to search through 3-digit numbers, which will radically increase my response times on my searches. So this is just one algorithm that we can use. The problem with an algorithm such as this is that if I have two numbers that are very close together, let's say that there is another student in my university, 4, 5, 6, 7, 9, that has this W number. When I apply my hash algorithm to it, they are both going to result in the same hash key. And this is called a collision. Generally, I would like to avoid collisions because the whole idea behind storing records in a database format is that every single one of the records has to be uniquely identifiable. And so I would probably want to change this algorithm somehow, make modifications to it, or come up with a different algorithm to minimize or reduce the number of collisions that occur. But sometimes there are value in the collisions that do occur. Sometimes I want to use those type of collisions to my advantage. Let's go back to the students. Let's say, for instance, that I have a classroom that has 5 rows of seat, and I wanted to assign the student to one of the 5 rows. Instead of just allowing them to sit wherever they want, I want to give assigned seatings, but I want to be fair about it, and so I'm going to attempt to assign them to the rows based upon their W number. I can use a hashing algorithm and the collisions that might occur in order to decide which of the 5 rows to assign the students to. This particular hashing algorithm, we're going to use a modulus operator, because if I need 5 rows, if I want to assign all of my students into one of 5 rows, a modulus operator is an excellent tool that I can use, because what I know of the modulus operator is that it gives me a remainder when I do division. And if I want 5 rows, if I were to use a mod 5 operator, the only values that a mod 5 operator would ever be able to generate for me as a remainder of a division are the values 0 through 4, which gives me 5. 0 to 4 gives me 5. And so what I could do is I could take each one of the students' W numbers, and if I did a mod 5 on it, it is going to give me a remainder. And that remainder could be the row that I chose to put the student in. Let's say, for instance, let's come back to 1, 2, 3, 4, 5, 6, 7, 8. This student, if I do a mod 5 with this student, what is the remainder going to be? 3. So let's take another student. How about 1, 2, 3, 4, 5, 6, 7, 9? If I apply the mod operator to this W number, this is going to result in a remainder of 4. So this student I'm going to put on row 3. This student I'm going to put on row 4. Let's do another student. How about 2, 3, 4, 5, 6, 7, 8, 9? If I do a mod 5 on this one, the remainder is going to be 4. Now this is actually a collision with the W number immediately above it, but that's acceptable because I wanted both of these students to be seated in row number 4. Now if I have 100 students and I'm going to have 5 rows, how many students on average would be within each row? Well, if I have 100 students in 5 rows, there are going to be approximately 20 students that are seated on each row, correct? So this is an example of a hashing algorithm where I'm going to take advantage of the collisions that can occur in order to assign my students to one of 5 rows. If I were to look at this problem a little bit differently, what if the original problem had been that I am in a classroom and I can have a maximum number of 20 students on each row? The classroom is already set up and the rows are only 20 students or 20 seats per row. How many rows am I going to need? Well, if I have 100 students and I can have the maximum of 20 students on each row, I'm going to take 100 and I'm going to divide that into 20, and that is going to give me 5. That means that I need to have at least 5 rows if the most number of students that I can have on any of the rows is 20. And so I would look at this as a potential mod operator. Now, for reasons that are outside of the scope of this class, I want to make sure that whatever modulus value that I am using, needs to be prime. And so I can use 5 as my modulus operator because 5 is prime. So let's say, for instance, that instead of 100 students, that I actually had 120 students. The most number of students that I wanted on any row was 20. When I do this division, I come up with 6, evenly divided by 6, but this is not prime, which means that I am going to move up to the next prime number. I know that 6 is not prime, but I'm pretty sure that 7 is prime. And so if I were to use 7 as my modulus operator, I have 120 students. How many students would I have on each row? And if I do this division, I'm going to have something slightly over 17 students on each row. Well, that is perfectly acceptable because the original premise, at most I could only have 20 students. And if I use 7 as my modulus operator, then at most I'm going to have, actually it would round up to 18. So the most that I would have would be 18 students on each row. And this would be acceptable. And so when I'm looking for a modulus operator use, I want to make sure that it is prime, and I want to make sure that the one that I use is large enough to meet the requirements. If I had gone back to my original modulus operator of 5, let's see how many times 5 goes into 120. This would be 24. And 24 students is too large for my original premise of only allowing 20 students on each row. So 5 in this particular instance is not going to work for me. But I can't use 6 because 6 is not prime. And so then I would do my calculations on 7. And when I use 7 as a prime, I can see that it would give me 17 students and some change. That would be, it's not evenly divisible, but I would have at most 18 students on each row.